Hello there.
Hi, Alec.
Hello, Peter. Can you hear me?
I can. Can you hear me?
Yes, also.
Great.
Just to share. Okay, basically, thank you all for coming. We will start in 1 minute. Sorry for being a bit late. Our previous session was quite extending, and the people had a lot of questions and wanted to answer. But right now we are here, and basically we are continuing with our program. To everyone, once again, thank you for attending. I think that we are also above 200 people all the time together on Facebook, our website, and together on Zoom.
Okay.
Basically, what is important thing to say that in this Fireside Chat, you will get a chance to listen to the interview with Peter Morgan, who happens to be CEO of Deep Learning Partnership. Also, Peter is acclaimed publisher with O'Reilly Media, experienced keynote and leader of data science, AI, and quantum community in London. He is also a very good friend and one of the key contributors to the Data Science Conference franchise, and we are very happy to have him in our team. Through this Fireside Chat, we will cover 3 important topics. First one will be what is quantum computing. Second one will be difference between quantum and classical computing. And the last but not the least will be what is the role of quantum computing in developing artificial general intelligence. Basically, I will just, for the start, I'll just take a second to see if we can start with it.
Okay. Shall I leave my video on?
Yeah, do you just keep your video on? And we are starting like in for 1 minute, I think, just to get a green light that everything is set up on the Facebook, so we can, everybody can see.
Yeah. So they can see you and I, our video. Yeah. Okay.
Okay, we can go. Basically, how is this session planned to be? Basically, it's going to be some kind of interview, let's say, or maybe a podcast would be a better word to say. What you'd like to hear, and we are let's say encouraging public to actively contribute to the talk, and we will try. Me and Peter and me will try to be very dynamic and to cover all of these 3 things we mentioned. So, on the first question, I would like to ask you, Peter, can you explain us for everyone who I think there is a lot of newbies in this field on this call, what is quantum computing actually?
Yeah, that's a good question. So quantum computing is like classical computing, except it uses the laws of quantum physics to do the computation. So those of you who are not quantum physicists, that basically means that it goes off into something called Hilbert space, which is basically how nature designed the universe, and it's available to us to do computation. And the reason we haven't done it yet is because it's quite a hard problem to engineer. Remember, quantum mechanics was only formulated in the last century, maybe 100 years ago, in the 1920s, Heisenberg, Schrödinger, etc., Bohr. And it's taken us about 80 years really to get to the point where we can actually build what we call a qubit, which is the fundamental unit of computation in a quantum computer. So it's just a hard engineering problem to get all these qubits to sit in a nice cold space where we can control them. And Richard Feynman in 1980 roughly was the first person to really come up with the idea or the notion that we could actually use, you know, the laws of quantum physics to do computation. And then from that moment on, people have been exploring what that means in terms of what we could actually do with the quantum computer, which would be different than what we can do currently with our classical computers.
Yeah, and maybe it will be a good thing if you can think about what would be the best parallel to explain the shift in paradigm between classical physics and quantum physics, or classical world versus quantum world, and maybe that will be good enough so people can understand why is that so different.
Yeah, so that's a good idea. So in a classical world we're all familiar with, that's our intuition, because we're classical, you know, objects, human beings, we're classical, living in a classical world. Everything we see around us is classical. We don't really see quantum effects unless we go into a lab and design an experiment to show us quantum effects. So at the fundamental level, nature behaves quantum mechanically. It's just once you have many particles, quantum particles, they kind of smear out into the classical world, what we see. But if we stay small and cold enough and get rid of all the vibrations, so these we can sort of see and work in the quantum world, we actually see quantum mechanical effects. Now, the difference between a classical bit and a quantum bit or a qubit is that a quantum bit can take an infinite number of states, whereas a bit can only be 1 and 0, kind of spin up, spin down, whereas a quantum spin can be anywhere on, imagine a sphere, on the surface of that sphere. So you get, it's almost like an infinitely more possible states, which is where the power of the quantum computation comes in.
Basically, like I was giving the interview, believe it or not, last 2 days ago for some of our mainstream media about quantum computing, and I explained to them, if you have a classical computer, you have 100 gigabytes, and you want to double the space of it, you need to have one additional 100 gigabytes, which is okay with 100 gigabytes. But if we are talking about 100 petabytes, it's not a good thing. But if you want to add 100 gigabytes to additional 100 gigabytes in qubit, you just need to add 1 qubit actually. Basically, so the power is unimaginable regarding that. So basically, my question next regarding that is like to maybe put a bit closer to the people who are the major players in this industry, and maybe what is their main achievement?
Yeah, so the major players are Google, IBM, Microsoft, and yeah, so those are the big players building quantum computers at the moment. And there are a lot of startups as well, like Rigetti Computer, Xanadu in Canada, IonQ. So, and there's you know, every country now actually has at least one quantum computing startup, you know, but the big guys are in China, it's Alibaba and, you know, Tencent, Huawei. In the US, it's the big cloud providers. Amazon are not building a quantum computer, but they're actually going to be the platform. They're going to put a lot of quantum computers on their in the Amazon cloud and offer it as a service. So, and so, as Microsoft, IBM already have 16 quantum computers in the cloud at the moment. You can log in today if you want to. Rigetti have one on the cloud. This year, Amazon and Microsoft have both announced they will offer quantum computing as a service using other people's hardware on their cloud platform.
I would like to. We have a question from the public, and I will give the let's say the advantage to the people who are attending than what we have as a script. So basically, like I said, I would like to keep this very dynamic. So basically, just to read again the name because it's not I'm not very familiar with this name. Basically, Shana was asked us about do you know about how to use deep learning in terms of quantum computing? Is this already something that is done, or something that should be done in the future?
Yeah, so that's something known as, we just call it quantum machine learning. And the big question is, can we use quantum computers to speed up machine learning or deep learning, as you say? The answer is yes. So some of the computation in the deep learning can be offloaded to the quantum computer, run on that, sped up with its, in the Hilbert space, many times faster, and then brought back. So the QPU, quantum processing unit, is almost like a co-processor to the CPU. Instead of offloading to a GPU, we offload it to the QPU. And that's currently how people are thinking of it. There may be more in the future, but it's a very new field, maybe 1 or 2 years old. So we're still investigating it.
Yeah, what I heard about that Daimler in Germany has actually one case actively working. That's the first case. Daimler together with IBM Qubit has already done it. I heard about them that they are already using. But I think that maybe this is a perfect time to maybe make a parallel and to explain to the people like we are talking about deep learning, that is AI machine or machine learning experts. Basically, what is your opinion about, and do you think it's possible to switch that easily, for example, from software engineer to quantum computer engineer?
Yeah, so that's a great question, isn't it? So, well, basically right now, because it's quite low level and we just started to build them and introduce them to the public, you know, without knowing a little bit about quantum physics, it'd be quite hard, I think, because we're kind of, remember classical computing in the 50s, it was all assembly, right? We didn't have compilers or high-level languages. So right now we're kind of at that sort of assembly, people are coding in that kind of level. Or we have to kind of understand what the qubits are doing. So the code is written in Python, that's okay. It's compiled down, but you really have to understand, you know, what these different quantum circuit, how to build a quantum circuit, basically. So that hasn't been abstracted away. People are working on that now, and there are various libraries like Qiskit, the IBM library, Cirq, the Google library, Rigetti have something called Forest. So, you know, every hardware manufacturer basically has this stack, like a stack with the Python language on the top. Normally it's Python. And then, you know, but you kind of have, at the moment, you have to know a little bit about how to build a quantum circuit and what they mean. There's different types of gates like Hadamard gate, you know, C0 gate. And those map directly onto quantum physics. So at this point, you have to understand what a gate, the C0, difference between a C0 and a Hadamard, you kind of have to understand a little bit of physics.
Yeah, and regarding that, you mentioned about the qubit and the still that is not functioning. Like I said, right now in machine learning, there is a proof of concept already developing in let's say in Invest Manager. But Nicola has asked one question: when in the future do you expect a fully working quantum computer? And I would like to add maybe what do you see as a fully working quantum computer by your opinion as an expert? What is fully and what is not fully? Where is the line for you?
Yeah. So right now we're up to about maybe 50 qubits. So we can log into the IBM computer on the cloud. They have a couple of 50 qubit machines. That will cost you money. The smaller qubits, like 4 qubits, are free. Maybe even the 20 qubit. I think you might have to pay for that as well. They do cost a lot of money because they're, you know, new and they cost 10 million to build. So, you know, they're not that cheap. So, but the lower number of qubits they're free. Okay, so the bigger question though, step back, how useful is a 50 qubit quantum computer? What can we do with it? Not too much really. At the moment they're noisy, and what we're aiming for is maybe 1,000 qubits. Then we can do some really powerful, meaningful computations, and low noise. They call that fidelity. The quality qubit quality is called fidelity, and, you know, all-to-all connectivity, and 1,000 error-free. So that's where we're going to. Maybe 5-10 years out, we'll be there. But right now we have 50 noisy qubits, and we can do a little bit like that. I mean, Google announced last year, I think October, quantum supremacy. So they used a sampling algorithm which outperformed the classical, you know, the world's largest Summit classical supercomputer. It did this calculation in 3 minutes, what would have taken the Summit computer. They calculated 10,000 years, and then IBM said, no, we could do it a little quicker, but it still wasn't 3 minutes. So we're already with 50 qubits, we've surpassed what the biggest classical computer can do on a very limited problem. So we just, you know, it's time now. We're on a Moore's law. So 50, then 100, then 200, then 400. So.
Yeah, I think I would like to hear your thought about. I have something regarding that, thinking, developing algorithms, etc. I think, and we have one question that I will follow up after this question on that. Basically, my personal opinion, what I can see that people are still trying to think in a classical way to use quantum computing, and maybe that is also one of the maybe the issues that we cannot still use maybe even better this 50, because our mind is still not approachable. We cannot still think about time as timeless, basically, like, or quantum entanglement, and what it doesn't mean, what is the capability of that. And we, let's say, we bound ourselves in some way that is not a quantum state like. So basically, we're trying still to put our classical computing, the quantum computing is still to try to put our quantum mind into quantum computing. That can be that can be a win-win situation, not the other way around.
Right. Okay. So once you do that, you understand that the four main applications of quantum computing is simulating chemistry, which was Feynman's initial vision, because chemistry is quantum governed by the laws of quantum physics. So a quantum computer will map onto that, and so that's the main application. Optimization problems like traffic routing, some sort of portfolio optimization and finance. So banks are looking into this, and machine learning, which we touched on briefly, and encryption. So a quantum computer can factor two numbers very quickly with something called Shor's algorithm, and that will destroy all encryption that we have now. That needs about 1,000 or maybe 10,000 qubits. But we'll have that. So banks are already, looking to quantum-proof their encryption algorithms. In fact, every system in the world that uses communication will need to upgrade there. So there's work being done there. So those are the four applications. But yeah, you're in a sense, it's, you have to, I have a physics background, so I'm used to thinking quantum mechanically, but it is something that you have to kind of do, I guess, to really understand what you're programming, right?
And regarding that, Anna asked a very good question, is how to approach programming on a quantum computer with base level knowledge of both physics and programming, in terms of what is the current state of quantum assembly level programming, and how can we translate such complex algorithms like deep learning into what quantum computer can understand, and let's say additionally can implement fully, like full power of it.
Yeah, so in terms of programming, what we have now, if you go online and into the IBM Q website, the Microsoft have what they call a QDK, which is a quantum SDK basically, and Rigetti have theirs. You can look at the libraries that are available to you today, and you can start playing around. You don't need a quantum computer. You can, just read through the code, read through the explanation about what the code does. If you want to, you can log into some of the smaller machines for free, Rigetti and IBM, and just play with it basically. So right now, yeah, you can start and sort of have a head start for when useful things can be done on quantum computers. So
okay,
there's a lot of material.
Yeah, I have one, let's say, two follow-up questions on that. That is also quantum computing is classical computing. And basically it is, can you give us some example of the problems that are solved with the quantum computer and not with classical computing? And maybe can you give us example in for like one or two things that quantum computer will never can even beat, not classical computer, but like home laptop, for example, because I know that there is some things that basically quantum computer is not meant to do.
Yeah, so yeah, I did mention the four different examples. I think simulating chemistry, so something like drug discovery, molecular dynamics, it's perfect for. But again, with 50 qubits and noisy qubits, we can actually simulate very, like, I think lithium hydride, H2O, a hydrogen molecule obviously is the simplest quantum mechanical system you can have, molecule. Basically. So yeah, we've actually done that, and we've plotted the energy spectrums, the energy levels of these very small molecules, and we've obtained perfect fits over the classical computation, which takes a huge machine, several days, and the fit's not very accurate. So already, quantum computers are outperforming classical computers. They're not good at everything, like, web development. That will still be done using classical computers. The way I like to think about it is that, the CPU will always be the central, we'll always need a CPU for quantum just to control. The control system will be classical processing unit. and the QPU will be a co-processor. So whatever we need to do, if we need to do a quantum simulation, we'll offload it to the QPU and back to the CPU. If we want to do a web page, we'll just have a CPU. If we want to do machine learning, we might have CPU, GPU, and then QPU. So we're looking at a whole bunch of different processors, like a system on a chip, except the quantum needs to be very cold and it's very big. So it's a slightly, they won't all go in the iPhone. The QPU will not fit in the iPhone. It'll always be on the cloud somewhere for the foreseeable future.
Yeah. Well, basically, I have one question and one, let's say, one question that is a little bit, let's say, controversial, but I will go first with the first one as an introduction. I was reading about a bit with quantum computing. We are not able to decode RSA keys, basic polynomial time equation that is used for basically encryption. I don't know if people understand how encryption works. Basically, it works with the background of unsolvable math problems, basically, to be used as one part of the equation for sure. And basically, regarding that, when we say that that is decoded already, that means like, I don't know, not maybe with 50 qubits, but let's say, imagine that we have that 1,000 or 10,000, doesn't matter. How do you see future of quantum cybersecurity or the cybersecurity at all when somebody can have quantum computing that can solve mostly all of the math problems in the background?
Yeah, so that's people are working on that. There's a competition at NIST in the US, and basically the competition is to come up with quantum algorithms. So right now, you're right, the classical encryption today over classical networks is done using classical encryption algorithms. And you know, that's a field, a mathematical discipline unto itself, and the math gets pretty hairy, and people have PhDs and whatnot to understand. But most of it involves factoring a very large number, like maybe 512 or 1024 digits long, and so that takes a classical computer like a century or more to do. Okay, they're not uncrackable, but it's just the amount of time, the sheer processing power. But a quantum computer can do that in a second or a millisecond. It's very good at factoring large numbers. So to get around that, we need to come up with quantum algorithms, quantum encryption, and that again is a discipline unto itself. So.
Yeah, basically, and what come across my mind, I was thinking about, and I was watching, of course, I was watching a lot of popular sci-fi, let's say, shows like Dells, which is basically Dells. I don't know if you watched that. It was very good show. I will send you a link after the meeting. It is awesome.
Yeah.
It is a little bit too far going with some things, but basically the concept is that with quantum computing powerful enough, having everything, having in mind that we have theory that everything in the multiverse is deterministic, can be deterministic. That means that we can change, we can basically predict what will be the possible outcomes with very large amount, with indefinite times in the future. Basically, the concept of the time is can be very totally differently used, and our view of the time is totally different. So basically, my question is, for this is, like I said, a bit soft, but also very important, like to people understand what paradigm and cultural change quantum world, the quantum computing, quantum ML can bring, really. When we don't have time, how we can, in your opinion, how will we have, for example, financial systems, so like trade, stock markets, etc. For me, I cannot understand, I cannot imagine that can influence that the world as we know like now can exist in like 10 years when we have 10,000 qubits, 50,000 qubits, doesn't matter, maybe 15 years, it doesn't matter. But what is your opinion about the future when the quantum computing is powerful enough to do what it can do?
Yeah, I think the greatest potential, I mean, is in, again, drug discovery. It's basically molecular dynamics. So if right now, deep learning, DeepMind beat the protein folding competition using deep learning algorithms. Quantum computing will be able to accelerate that again. So, by modeling molecular dynamics of large molecules, if you have 10,000 qubits, you can basically model 10,000 atoms, right? That's a large molecule. It's not quite DNA, but it's still a large molecule. Now, that's probably enough to discover some good drugs, maybe cure cancer, coronavirus, etc., etc., etc. So this is really the vision in people's minds. This is where we want to get to as quickly as possible. And so there is a lot of money being poured into this. These big companies, like I mentioned, Google, IBM, Microsoft, are basically pouring billions in. And the Chinese have just put 10 billion into a big quantum computing center that they've set up. So these are massive projects. And in the national labs like Los Alamos, etc., there's a lot of money going in there. You don't hear too much about it, but it's such a powerful form of computing and a totally new paradigm that people really understand. You don't want to get left behind here. In fact, you want to be out in the lead. So there's a bit of an arms race going on right now.
That was a good paraphrase, let's say, parallel. That is basically very similar to the like what was like the moon race in the 1960s through the Cold War situation. Basically, now it's the same. Like people cannot because there is a lot of, let's say, genius people who are working on that. There was genius people also during the 70s, like you said, Feynman, but they didn't have like technology to build something like that. Like, and that was the issue. Right now we have a technology that can, okay, slowly, but it can, like you said, like it will be very fast and fast. Like my personal approach to that will be, let's say, it will be very, very like let's say, the next big step, like it will be like smartphones and steroids, like what the change it will be. And one of the questions also from Anna was also in the terms of educational systems. Do you think that quantum computing and what does the education system need to do to prepare for the changes that quantum computing will bring? Not only like in the terms of using quantum computing, but like I said, the change of in the world as we see it. Do you think, what is your opinion on that?
Yeah, so I guess, it's started to be, some universities are starting to offer undergraduate courses, or at least putting a one semester of quantum computing in, right? So, either the computer science curriculum or the physics curriculum. So currently in physics, you might have information theory or statistical mechanics or quantum mechanics. In computer science, you'll have, some algorithms, but they haven't got a fully semester dedicated fully to quantum computing. Now this is changing. I think MIT, Caltech, Princeton, perhaps Oxford, they actually have now introducing this into the syllabus. So, I mean, this is what we need to do, is to teach people as undergraduates and certainly as PhDs now, to make sure that we've educating the right number of people. We're going to need thousands, if not 10,000s, right? Just like, we have today millions of classical developers, we're going to need the same. It's a new paradigm in computing, and it will grow as big as the classical computing ecosystem in terms monetarily, number of programmers, applications. It's not happening today. We're very early, 50 qubits, but we are on a Moore's law, and we've learned a lot from the classical computing. The last 70 years in classical computing, we know how to build frameworks. We know we've got GitHub. We have a whole bunch of knowledge, so it might happen a little quicker, I think.
Of course, I think. Yeah, and also what is important thing to know that one of the hottest trends for everyone to know, one of the hottest trends, but really in quantum computing right now is investment, developing talent in academia, because people understand that they need to, it will have quantum computer engineers will not be able to move forward, because it is totally different paradigm to do classical computing algorithms and quantum computing algorithms. That is like different paradigm, and you need to have a different opinion, and you cannot work on both at the same time. It's basically like, okay, maybe you can, but that means that you're not 1%, but you are 1% of 1%. Like you can do that a long time. You need to be like Einstein or something like that. Okay, we have one question before we forward. Okay, Nicola has.
Yeah, I'll just say there are a couple of good books. Bob Souter at IBM has just written a book called Dancing with Qubits, available on Packet Publishing. Jack Heddery from Google has written a nice book on quantum computing application. Now these are aimed at beginners like you and me, right? So you can open it, you start at, hello, well, here's linear algebra, here's a qubit, here's a circuit, so there are books out there now, so you can learn.
Yeah, that's right. But it's very easy to find a good material for beginners. And basically, that can be sometimes it can be a bit advanced. You need to know a bit more about quantum mechanics. How like to go to the not quantum computing but quantum algorithms already. You need to understand a bit more. And regarding that, and one of the questions is also referring to that. And what is one of the main things in this fireside chat is this. Artificial general intelligence, and as one of the, let's say, do an intro to all of our attendees, what is for you artificial general intelligence in terms of how would you describe it? Where are we now with developing AGI, and what do you think? How long should we wait for it?
Yeah, so people are working on that as well. There are groups of people, academia, DeepMind, for example, Google, Microsoft. They've all got, you know, again, this is the holy grail. This is the big vision, is to build not narrow AI, which deep learning is, image classification, but general intelligence. And it has been a division since the 50s, right? Marvin Minsky, you know. So, I mean, there's a whole bunch, McCarthy, Minsky, there's a whole bunch of people in the 50s had this vision. They had a summer school in New Hampshire, and they kicked the whole field off, right? And here we are 70 years later, and we haven't built it. So clearly it's a hard problem, okay? I think those guys thought they would solve it in 10 years. I really do believe they could. Now, clearly the brain, which is artificial general intelligence, is so complex that, and we know now it's 100 billion neurons and 1,000 synapses for each neuron. So we're talking 100 trillion synapses. Now that's a complicated system. So this is why it's taken 70 years. It was never going to take 5 years, right? So they were just a little bit over optimistic. So we're still a little ways away as well. You know, DeepMind are coming up with algorithms and whatnot, but really they haven't cracked it at all. There are a lot of academic groups that probably we don't have time to go into, but you know, it's an ongoing theoretical work at the moment, and no one's built, you know, a processor that, you know, here we are, here's AGI, we can run it there, you know, that hasn't happened yet. There's neuromorphic processors, which are biologically inspired. Maybe they're the way to get there on a hardware perspective, I think. So we need to look at the brain. We need to understand the brain a little bit more, Alec. Yeah.
Basically, yeah, that is completely right. Maybe I think that this is the perfect, like, before we go to the question from the attendees, maybe it will be a good thing maybe for you to maybe just briefly explain the difference to our attendees between narrow artificial intelligence, artificial general intelligence, and super artificial intelligence. I think that people don't understand the difference between these three terms, and that's why they're all the time thinking, okay, we already have it, it will be 5 years from now, 10 years from now, 100 years from now, and basically they are talking about three different concepts actually, and what does it mean. So maybe briefly just to explain as the, like I said, intro to this topic.
Okay, so artificial general intelligence, again, we are, you know, general intelligence. We are trying to build a system like ourselves, and that includes sentience and consciousness, self-awareness, subjective experience. Unless you have that, you're not fully generally, that's not general intelligence. So we're a little ways off that, aren't we? We have not built some hardware which becomes conscious. And there's nothing in physics that says we won't, but you know, we're not quite there yet. What we do have is narrow AI, which is basically deep learning, which is artificial neural networks, which is basically just statistical analysis. Okay, it's nothing to do with what the brain does at all. It has to see a million images of a cat to understand the next one's a cat, right? We need to see one image. They take 1 million times more power, and they can do about 1% what the brain does with deep learning. Okay, so that's a dead end. That will not ever get us to AGI at all. So what will get us there is the neuroscience approach, maybe neuromorphic processors. That will get us there. So sometimes there's so much stuff in the press about deep learning, and everyone's suddenly called it AI, which is just, that's why everybody gets confused. It's not AI at all. It's just the statistical analysis, and you need a huge amount of compute. You know, in fact, it's contributing to climate change. It's definitely, we do everything on 30 watts. We can eat a sandwich and come up with a theory of relativity, right? There's nothing to do with deep learning. This is what confuses people.
That's an awesome parallel, actually. That's the first time that I heard this kind of parallel, but it's really like, it's very, very cool to have this kind of parallel. And basically, we have a question from public, from Nicola. He was asking how much does quantum computing can help in solving some MP hardness problems, like, I don't know, traveling salesman, or in training of some really large neural networks. And of course, the question is, and can it help it the road towards AGI?
Yeah, so that's a good question. Yeah, it can help speed up some deep learning, but again, that's nothing to do with AGI. Now, so the question really is, does the brain use quantum physics to, do what we do? Do we use quantum physics, or is it just such a wet, squidgy thing here, 1.5 kilos on our shoulders, that all the quantum physics is smeared out? So it's just purely classical computation. Well, Roger Penrose would argue that actually at the microtubule level, we are using the laws of quantum physics. And in fact, consciousness arises simply from that. Now he's a little bit out on his own on that, but he's also a very clever guy. So maybe it's just going to take the rest of us 10 years to catch up with what he's doing. So there, yeah, the jury is out really. Now, I don't know. I think the brain is a classical object, so maybe the quantum computing can help speed up some of the processes, but unless we go down to the microscopic level, which Penrose says we do, okay, he's saying we must, then obviously the quantum computer will model at the microtubule level to give rise to consciousness. Now, this is a little bit controversial, and there's some pretty vicious pushback sometimes. So I don't really want to go there, but that's the only way a quantum computer would be needed, I think, at the molecular level. Yeah.
Okay, that sounds yeah, a bit too far, but basically, you've covered that. Why is quantum computing important for developing and running AGI? I think that you covered that up. That basically, what's your, not your opinion, but what is the expert opinion on that matter? But maybe I can tell you. Maybe you can tell us more. Do you believe it is possible to develop AGI without the quantum computing? Maybe to maybe put it the other head this question.
Yeah, I think most people are developing AGI assuming, under the assumption that we're just going to need the fundamental building block of intelligence as a neuron, which is made up of, maybe a billion or so atoms. So it's actually too big. We don't need a quantum computer if we start there. It's like already a classical system at that size, at that scale, okay? And it's warm, and it's wet, and it lives in the brain, so it's not really a quantum system at that neuron level. So most people, I think 99% of the people in the world are starting at that level. The neuroscientists would start there. Now, because Penrose is a physicist, he immediately just goes straight to the quantum, kind of level. And so maybe he's right. We don't know yet. It's a little bit of a tricky situation.
Yeah, it sounds interesting. I will investigate after this talk a bit more about it. I wasn't aware about that. I'm also new in this field, like basically. But maybe before I ask one last question, which I think that it will be also very cool for people to hear your opinion. But maybe if you can tell us a bit more about quantum computing community, also how it's developed, who are there possible people with whom we can connect and stuff like this.
Yeah, so I did mention these big companies want people to use they're anticipating their 100 qubit machine on the cloud, and therefore they're wanting, just like Google, Amazon, and Microsoft all want people to use their cloud, right? Amazon wants you to use Azure, not Google Cloud or Amazon, vice versa. They're all wanting you to use their quantum system, okay? So they all have great educational material, basically. So you can certainly, there's a lot of stuff on the internet. And once you get over the quantum weirdness that is quantum mechanics, right? And it's kind of fun to learn, after that, it sort of becomes like an engineering programming problem. Once you get your head around the quantum bit, then it becomes, ultimately, people will just be, quantum developers will be programmers, right? At some level. We're not quite there yet, but, you just need to get your head around the quantum physics part, which isn't that hard. It's not really.
Maybe for you it's not. Joking, of course. But the thing is, I totally agree. I believe that without a good engineering part inside of you, if you don't have engineering yourself, even like if we're speaking about AI, you can do that until everything is going fine. But the first time you have a real problem without understanding of deeper understanding of, let's say, what is under the hood, basically, and for me, that is something that is very, very interesting, basically. I'm not sure how you can understand why the input is so what it is, basically. I don't believe in everything to be a black box. Like, personally, that's my approach. If I don't understand something, I will not use it until I fully understand it. That's my approach in life. Like, because when the problem comes, I will be very prepared to really think about it and provide my answer. So, like, I totally agree on you regarding that engineering part should be and should stay maybe in the future also regarding computing.
Yeah, so with me in deep learning, I had to learn that from scratch. Maybe 6 or 7 years ago I started. But after a while you develop an intuition. The same will be true for quantum. The more you do it, you just have to develop an intuition. So, hit the problems, debug them yourself, spend 2 or 3 days pulling your hair out. But eventually, you get a feel for it. So it's going to be the same.
Well, I don't believe that there is any better like feeling than when you realize that there was something, a really small mistake that this is very stupid from myself. How didn't I see this? And you're very happy because you found out that you're stupid. Basically, that's in the programming, that's the best thing ever. But one final last question. We already this 45 minutes was like a roller coaster. It already like passed. I cannot believe that, to be honest. It was like 5 minutes for me. Basically, this one, let's say, popular culture question. It can be a little bit hipsters or Elon Muskish. Should we be afraid of artificial general intelligence taking over control of our life?
Yeah, so again, everything's on a curve, right? Yeah, I mean, so when we build these systems, artificial super intelligence, we don't really know, right, what's going to happen. It's the uncertainty, it's fear of the unknown. So I think it's right to be fearful of things you don't know about. Okay, it'd be irrational not to just say, oh, it's going to be great and it's going to be beautiful, wonderful in a perfect world. Because, what happens if a mistake's made and, you have to debug it and you can't, and but the thing is, we're not suddenly just going to be there, right? It's going to be on a curve. So I think as we go along, our understanding will get more and more. And personally, I'm looking forward to superintelligence. They will be able to, solve a lot of science problems very quickly. Cancer, all sorts of stuff, right? And with quantum computers to simulate and superintelligence to operate these quantum computers, I mean, it's going to be a different world, maybe in 20 years than what we're used to. That's how I kind of go to sleep at night. I just think like that. It's going to be a different world.
And because we already talk about positive stuff about the quantum computers, etc., can you imagine right now one thing that you can see that quantum computing can be misused?
Yeah, probably cracking encryption, using it. Say somebody forgets to upgrade, and somebody spots that and just uses a quantum computer to drain, all the bank accounts. That would be very bad. So yeah, that would be a bad one.
Somebody say pioneer in Wirecard, or nobody's talking about it anymore. Okay, Peter, if there is no other questions, and I see that there is no, I would like to thank you all for, first, Peter, thank you for this inspiring fireside chat. For me, it was like first time I'm doing something like this together with you, and it was totally brilliant. I think that we need to do something like this more often because I was personally enjoying it. I hope that also our participants and attendees also enjoyed as much as we do. or as much as half as we do. What is going to be next on our let's say on our program? We now have 1 hour of lunch break, because we are not robots. We need to rest for a bit, and after that we are starting with the next data discussion. It is going to be AI monetization. It will be very, very awesome, because we are going to talk about very concrete stuff about how can we monetize AI successfully. We will have speakers who really done that. We are going to talk about how the successful AI project really looks like. And one important thing, what are the major obstacles? Why doesn't AI go more into production? I think that is very important to talk about this kind of question, because some let's say research say that only 2 or 3% of the AI projects go into production, which is really, really low. And you can hear it from experience, like all of them have more than 7 to 10 years of experience. So basically they will give you excellent overview of that. So thank you once again for attending this. We are seeing each other back at 1:15 Central European time. Thank you, Peter, once again.
Thank you. Bye.
Bye-bye.